Good morning, guys. How are you? I hope things are going well. So we're going to talk about Lecture 1 today. These are from the slides that have been uploaded to D2L. So hopefully we can get through that without too much of an issue. Again, if you run into questions, comments, problems, anything like that, there are places in the lecture where I typically stop to ask for those. Obviously, we can't do that in this format. So if you have a question, please take note of which lecture it is, the rough timestamp of when it is, and then send me your question, comment, problem, and I'll do my best to address that. I appreciate it. Thanks. So starting with lecture 1, we're going to go ahead and share my screen. Bear with me just a second. And now we're looking at our slides. Woohoo! Go, we made it. So when we talk about matter, there are a couple of classifications that we need to look at. We'll look at its physical state, and we'll talk about its purity. Okay, so we're going to look at its physical state in the next slide. The purity we'll talk about on slides 5 and 6. And we need to be able to talk about how pure it is to be able to classify that material. When we talk about properties of matter, we talk about the physical properties. They can be observed with no changes to the material. So these are things like color. These are things like a mass, if we wanted to take that. Things like a volume. Things that we can measure without any changes to that material. Chemical properties require changes to the material to observe, so we cannot recover the previous material. For instance, if we were to analyze something via mass spectrometer or something of that nature, we wouldn't have the same material at the end. Okay, that is a destructive mechanism, so that's a way to look at the chemical properties. We can talk about intensive materials, which are not dependent on the amount of material. Temperature, melting point, density are all intensive. So it doesn't matter if I have a giant sample of that or a small sample of that, they're the same. Anything that's extensive depends on the amount of the material. So the mass and the volume of that material are going to be dependent on how much you have. Adding more will change that. All right? When we talk about states of matter, we typically talk about three things: solid, liquid, and gas. Solid molecules are held in a fixed pattern. We can then melt that to get a liquid where they're packed closer together, but they can move. Okay. We can then vaporize that to get a gas. So things are free to move, but they're highly separated. All right. We can go from a gas to a liquid by condensation. We can go from a liquid to a solid by freezing. Okay. We can also go from a gas to a solid through a process called sublimation. All right. So those are the states of matter that we typically talk about. We also have plasma, but we typically don't talk about that in this course. So beyond that, we have to be able to talk about a couple of different things. So an element cannot be further separated by chemical means. A substance is a form of matter that has a constant composition and distinct properties. Okay, that says nothing about what it's made out of. So a substance is constant composition, so no matter where I sample from it looks the same, and it has a distinct set of properties. Awesome. An element cannot be further separated by chemical means. Elements are things that we find on the periodic table. And I always do this because there's a periodic table on my desk. So things like hydrogen, nitrogen, oxygen, things like that. We can't break them down any further. However, some of those things that I just mentioned, oxygen, typically does not exist on its own. So O2 is the way that we typically find oxygen in the atmosphere. Right? It doesn't exist as O by itself. That is not an element. That is a compound. Okay, even though we have two things that are exactly the same that make that up, okay, we cannot break that down without doing something to it, which then destroys the material that we were looking at. All right, so that's called a compound. So it's no longer an element, it is a compound. All right. Then we have things called mixtures. It's a combination of two or more substances which can be separated by physical means. What are we talking about there? Well, sodium chloride. How can I separate those things? Let it evaporate. And what will you end up with? A bunch of sodium chloride, table salt, and the water will be gone. The water will have gone into the atmosphere and we won't have it to collect back. I mean, it's possible to collect it back, but that is a way that we can separate it by physical means. So things that we do that with, evaporation is one of those things, filtration is one of those things. So there are a couple of different physical means that we can use to separate them, okay? And that's something you'll talk about in the lab. So elements, compounds, and mixtures. All right, we talked about those. So let's look at this particular set of images that we have here. So an element is something that cannot be broken down into anything smaller. So this is an element. I have one single thing making this up, and therefore that's an element. I don't know what element it is, but it's an element. What about this guy? Two things made out of the same thing because they're the same color and the same size. But I can break those apart. And so I can break that down. That therefore means that this is a compound. Okay. This particular thing, again, I have one element in the middle, three outside elements that are the same because they're the same color and the same shape. All right. All of the things in this particular box look like that. So that is a compound. Now, if I come down here and look at this image at the bottom, I have different distinct things present. So I have some elements in here, I have some compounds in here, I have some compounds in here. So this is a mixture. Okay, chances are we can separate this by physical means. All right, so that's what we're looking at. It's just another way for us to visualize those things. These are what we call space-filling models, and they are something that we use from time to time. The colors that are there, you may not know what they mean. They may not actually tell you what they mean, but they do indicate whether it's the same material or a different material. Different colors mean different materials. The other thing is relative size. Seeing if they're the same size or not will tell you if they're the same. Okay, so measurement. Obviously, that's a big deal. We do that a lot in the laboratory. If there's something I want to measure, I need to know a few things. What am I measuring? And how accurate is that measure? Okay, so what the heck? And I put another thing. What are the units of that number? Why do I say that? Because to me, units are incredibly important. You'll see that every time I do a mathematical calculation, I include those units. There's a reason for that. And so a number should not exist without a unit. Okay. So if I'm trying to measure something, how am I trying to measure it? Do I want to know its mass? Do I want to know its volume? Do I want to know the density of that material? And of course, in order to do that, I need to know what am I trying to measure, and therefore what are the units of that measurement, and that'll tell me what kind of instrument I need to use to measure that. So if I want to get a mass, I know that I'm going to need a balance because that measures things typically in grams. Grams is a unit of mass, okay? And how accurate is that measurement? What does that mean? Well, it's easy to see if I'm looking at a balance because the balance has a fixed number of decimal points that it will spit out at me. That's how accurate it is. But that's not the only thing that we have to talk about, and I'll show you an example of that in just a minute. Let's talk first about the base units. So this is one of the things that we were talking about just a minute ago, is how do I know what I'm trying to measure based on the units that are present, or based on what I'm trying to measure, what are the units that I need to look at? These are the base SI units that we typically deal with. Length is a meter, that's the standard one. Mass is a kilogram. Time is measured in seconds. We have a couple of things down here that we don't really talk about, so we don't typically talk about electrical current, the amount of or the luminous intensity. We do talk about the temperature, which is listed here as Kelvin, and the amount of a substance listed as mole. Okay. Now, are these the things that we commonly use? No, but those are the standards. And so we need to be able to move between those standards and things that we typically use, like centimeters, millimeters, decimeters, milligrams, kilograms, grams, Kelvin, degrees Celsius, degrees Fahrenheit, seconds, minutes, hours. All of those conversions are things that you're going to be expected to be able to do. Okay. One of the ways that we talk about that is this prefix. So I mentioned meters, centimeters, meters, millimeters. Okay, so that's all based in this table that we have right here. So if a meter is listed as an M and a millimeter, right? So milli is listed as an M, okay? So a millimeter is mm, right? Just like we see here, millimeter is a milli, 1 m for the milli, and then 1 m for the meter. And 1 millimeter is 10 to the negative third meters. Okay, I don't like to do it that way. If it's a negative exponent, I'm not a huge fan of that. Instead, what I'll do is I'll say that there are 1,000 millimeters per meter. Please understand that those two calculations are exactly the same, provided that you've put them in correctly. And I'll show you how to do that in a bit. All right, but you need to be familiar with these things. You definitely need to know centimeters and millimeters. You definitely need to know kilo. Okay, those are the ones that we use the most often. Typically, I mean, if you get another one and you don't know what it is, typically you can ask or look it up. That's usually pretty fine. But those are the ones that I know that you're going to need to be able to work with. Okay. Scientific measurement. We measure a lot of things in chemistry: length, mass, time, temperature, the amount of substances. Now, I said mass. Mass is correct. Weight is not. What the hell is the difference? Does it really matter? Yes and no. Okay, does it really matter? Yes, I think so, because I'm a scientist, so I think so. But when I talk about my weight, that weight is dependent on me being on the surface of this planet. So weight is how my mass is affected by the force of gravity. So my mass will be the same here as it is on the moon. My weight will not be. Okay, and that's why we need to talk about the difference, because it is important that you recognize that even though we talk about weight all the time, weight is not actually the way that we should be talking about something. We don't go to the balance to weigh it. We go to the balance to mass it. Okay, and even though there is an effect there from the force of gravity, it's one that we can take out because it normally comes out in the wash. Okay, so it's not that important. All right. Standard units are defined as below. Terms below were defined on slide 11. Mass is measured in kilograms, metric unit kilograms. Length is measured in meters. Time is in seconds. Temperature is in Kelvin. And amount of substance is a mole. And we'll get to some of those in a bit. 1 kilogram is 1,000 grams. 100 centimeters is 1 meter. 60 seconds is 1 minute. Kelvin equals 273.15 plus degrees C. Now, if I need to go from degrees C to degrees F, or from degrees F to degrees C, then I need a slightly more complicated way to do that, although most calculators can take care of this for you. You just need to figure out how to do it. It is possible. I'm not going to tell you how to do it, but if you can figure out how to make your calculator do it, then you should be okay. Now, here's the caveat to that. You need to be able to show how you set that up to be able to get full credit for it. Just because you get the right number doesn't mean you get all of the points, because on a test, we're looking to see that you understand the process of getting from one to the other. And if you can't show me that process, then it doesn't matter that you got the right number. Now, a mole is defined as 6.022 times 10 to the 23rd particles. All right, that number of particles is important. Okay, and this mole is something that we're going to talk about all the time. All right. Now, why do units matter? Why do I keep talking about the units? Well, let's just say that I have 12. I want that amount to be converted to moles of substance to do a calculation. So I have 12. Can I do that calculation? No, I can't. Why not? Because 12 what? What do I have? Do I have 12 atoms? Do I have 12 particles? Do I have 12 moles? Do I have 12 grams? Do I have 12 kilograms? I don't know. And that's why I keep coming back to this whole units thing. We need to make sure that units are included with numbers. Numbers by themselves have no context and therefore are not useful. Now, there is a part in your textbook which you can look at. It's the chemistry and action section in section 1.7. Why is that important? Because it shows you how important it is that we have those units listed. These scientists made an assumption about what a unit was, and that ended up making their measurement completely off. So instead of having this space probe go to the surface of Mars to be able to take measurements, it didn't hit the surface. and it was actually destroyed in that process. Okay, so we need to make sure that we know these things. You cannot make assumptions, because even if you're looking at the lab manual and it says that you're supposed to measure it in grams or whatever, it doesn't mean you actually did. So you need to make sure that that number has units associated with it. If I see a number that has no unit associated with it, you will lose points. That's how I do things, and it's because it's so important. All right. Derived units. Well, okay, so we talked about length, we talked about mass, we talked about a couple of other things, but not everything we want to measure is available in those units. If we wanted to talk about area, that's a length squared. Volume is a length cubed, so meters cubed is the SI unit for that. We don't always talk about that in terms of those units. Meters cubed is useful, but we often talk about it in terms of liters, and so you need to be able to do that conversion. Density here is listed as kilograms per meter cubed. We don't usually use that. Density is a mass per unit volume. For solids, we often list this as grams per centimeter cubed. For liquids, typically grams per milliliter, and for gases, grams per liter. Okay, I need you to understand that all of these are derived from our base units. The units are combinations of the 7 base units described. And so it's just something that we can do. Now, when you're doing calculations with these things, it's often, even though we have kilogram times meter per second squared is a Newton, if I need to do conversions on that, it's often more important that I list it as kilograms times meters per second squared, okay? Because that way I can do conversions and see the units. Any questions, comments, problems on any of that? Okay, awesome. Let's keep going then. And again, if you do have questions, let me know. Precision versus accuracy. Okay, I have 4 images here that I've given you, and they have some little things underneath them that talk to you about what they actually mean. So if I look at this, sorry guys, if I look at this first unit, it says that it's precise, but it's not accurate. So precision means that I have a very close grouping of all of those points, but it's not in the center of that bullseye, so it's not accurate. Even though they're all measured about the same, I didn't hit what I was trying to hit. So it could have a systematic error in how it's being measured. So even though the numbers are close to each other, it doesn't mean it's the right number. Okay, so that's precise but not accurate. Now I can have accurate numbers that don't group together well, and that's an accurate number with little precision. Okay, so we get variation around that number. It's actually pretty normal if you're doing something right. Okay, if you're measuring something in the right way, we get this kind of lack of precision. We hope that it's not a huge one like this, but it does happen. Okay, if I look at this third grouping, none of it's in the center and none of them are close together. So I have no precision and no accuracy. Go, awesome. This last one, all of my points are tightly grouped and they're in the center of the bullseye. So I have both precision and accuracy. All right. Now understand that I could have any of these situations at any given time when I talk about a number. Why do we care? It depends. I mean, typically you don't care. We just take the numbers for what they are. But this is something you need to be able to recognize when you're trying to evaluate data. So if you have a bunch of data that's really, really close together and then one point that's not very close to that, what does that mean? Typically that we would call that an outlier. But the question becomes, is that outlier a real outlier or was it something else? You know, is it possible that that is a realistic value that should in fact be there? So that's what we're talking about in those terms. And then that we typically leave to conversations in the lab. Okay. Scientific significant figures. Why do sig figs matter? Now, if you watch the sig figs lecture, you'll recognize this slide because I used it there. But again, it has to do with the precision of the number that we're looking at. Okay. So how well do I know that number? Okay. How many decimal places do I know it to? How, you know, how close to the actual value is it? Okay. So that's what we're talking about with this. So we can estimate precision to 1 decimal place past what we can actually read. All right. So if I look at this first ruler, I know that I have centimeters and nothing in between. That's the only thing that's actually there. This one, I have centimeters and then 10 gradations in between them. So I can get a lot closer to what an actual number is on this ruler than I can on the one that only has the centimeters. If I only have the centimeters, I can look at this clip and say, well, it's definitely more than 2. It's definitely less than 3. It's more than a half. So I could estimate that as 2.7. Okay. That's how I'd guesstimate it. If I were to look at this one, I know that it's more than 2. It's less than 3. That hasn't changed. But now I can go 2, 5, 2, 6, 2, 7, and it's slightly above that 2, 7. So now I know it is actually 2.7, but it's 2.7 something slightly higher than that, 2.72, because I'd say it's less than halfway in between the 7 and the 8. Okay, so that's what we're talking about. We always estimate 1 digit beyond what we have actual numbers for. We always estimate precision to 1 more decimal place than what we can directly read. Okay. This is the same example. We're just doing it in terms of 20 and 30 centimeters on ruler number 3 and 20 and 30 centimeters on ruler number 4, but there's more gradations on ruler number 4. The same thing is true though. So it's higher than 20, lower than 30, more than 25. And again, I would guesstimate 27 because it's closer to the 5 than it is it's closer to 25 than it is to 30. So I would say 27. If we look at it on ruler 4, I know it's more than 20. I know it's less than 30. I know it's more than 25. I know it's less than 30. If I look, it's 27, slightly above that. Similar situation to what we were talking about before. So I could guesstimate that as 27.2. Okay, that's what we're talking about. And that's the expectation in the lab, is that you actually do that, because that gives you the most accurate number you are capable of getting. And we know that there is some error that comes with that. That's something we can talk about in terms of propagation of errors, and I'll show you that, but I won't expect you to do it. Okay? Sig, figs, and rounding. Okay, so I have a significant number of figures. Why do I care? Well, for that one number, that's how you measure it, right? But the other thing is that I need to be able to know how many of those numbers in a number I've been presented are significant. First thing I'm going to tell you, zeros are not always significant. So non-zero numbers are always significant. Zeros may be. So non-zeros always are, zeros may be. Zeros between non-zero numbers are always significant. All final zeros to the right of the decimal are significant. Placeholder zeros are not significant. To remove placeholder zeros, rewrite the number in scientific notation. And rule 5, counting numbers and defined constants have an infinite number of sig figs. Oh my God, that's a lot of words, and I don't know what any of that means. Well, let's see if we can put that into some context. So non-zero numbers are always significant. So if we look at this particular example, the non-zero numbers here are 1.5. These are all zeros, so 1.5. Awesome. So both of those are significant. That gives me 2 sig figs in this number. All right. Now, the zeros, that depends. Now, these are past the decimal point. The ones in the first one are past the decimal point. So those are all important. All right. But to put this into scientific notation, we can go 1.5 times 10 to the 4th. Okay. That does not include the significant digits, because I know if I was really looking at this in terms of sig figs, that those zeros out here would be part of that. Okay. Actually, oops. So this is an example going from scientific notation to the actual number. So we're just adding those zeros to get to the right place. Sorry about that. I was looking at this as the actual number, and it's not. So 1.5 and then times 10 to the fourth. We have 1.5. We add zeros, and then we move this 1, 2, 3, 4, and then this is the final result. This is the number that would actually represent. I apologize for that. Here we have 5.8, okay? This is 10 to the minus fourth. So I write 5.8. I have 4 zeros to the left of this, and I move the decimal point 4 positions from where it is to the left. 1, 2, 3, 4. And this is our final result. Okay? Does that make sense? Sorry, I hope that I didn't confuse you too much with the first one. All right? Now, let's talk about these. Let's talk about scientific notation here. I want to practice. So 2.13 times 10 to the third. So I know that I'm going to have to put some zeros out here because I have 1, 2. I need a third place, right? So 2130. And then I go, the decimal point is here. 1, 2, and then one more to go past that 0 that I've placed there. So that's 2130. 7.5 times 10 to the minus fourth. This is one place. I know that I'm going to have at least 4 zeros out here to make that work. And then I move the decimal place from the behind the 7 where it is to 1, 2, 3, 4. Okay. And again, since it's negative, I'm moving it to the left. If it's positive, I move it to the right. Awesome. 9.8 times 10 to the 6. Now, when it's positive and I have a number here, I only need to add 5 zeros. Okay, because I have one place that I can do with this. So I have 9.8, 0, 0, 0, 0, 0. And then I move my decimal place. So 1, 2, 3, 4, 5, 6. And this is the number that I end up with. Okay, 5.67 times 10 to the minus 8. Again, I need to have a bunch of zeros out of the front, and that should be 7 of them that I need to add. So 5.67, I move from here 1, 2, 3, 4, 5, 6, 7, 8. And this is the number I end up with. Okay? Now, total volume, yada, yada, yada. Okay, why am I looking at this? Well, I have 4 sig figs total here, right? Because the number in this 0 in between these non-zero numbers is significant. I have 4 sig figs here. Awesome. So I know I have 4 sig figs in both of those. But I'm doing addition on this. So I add those numbers together. And how much, where do I run out of precision, as it were? So both of these are 2 places beyond the decimal point. So that's where my number needs to be rounded to, 61.80. So that 0 needs to be there because it is significant. Notice it's to the right of the decimal place, so it does matter. And I can't just drop it, because if I do, then I have the wrong number of sig figs. Okay. For subtraction, we do the exact same thing. Again, we have 49.06. I have 4 sig figs, 2 beyond the decimal point, 4 sig figs and 12.74, 2 beyond the decimal point. I do the subtraction, I get 36.32. That's 4 sig figs total, 2 beyond the decimal point. So that's the correct number of significant digits. If I wanted to do multiplication, I can do 49.06, again, 4 sig figs, 2 beyond the decimal point, times 12.74, 4 sig figs, 2 beyond the decimal point. And I end up with 625.0. Now, why is this not just 625? Because 625 is only 3 sig figs. I need to have 4, because both these numbers have 4 sig figs in them. So that 0.0 is important, okay? Same thing is true when we do the division, all right? We get a 3.851, and we keep 4 significant digits because I have 4 here and 4 here. Now, I told you we were going to talk about that error, so the estimation that we did before. That uncertainty is what we're talking about. So I know that that number that I reported is plus or minus 0.05 if I'm talking about this particular number here. So I know that there's inherent error in this. And I see that they're talking about this as being additive and putting this into 0.1, and then we report that as part of the number. We're not going to do that. But I need you to see that we know that those numbers are not accurate and that we can look at the propagation of that error by doing these kinds of calculations. It can be done, all right? So that's why that matters. Let's talk about dimensional analysis. Woohoo, dimensional analysis. Now, what are we talking about here? The factor label method for converting units. Yay. What the hell does that mean? The factor label method is a sequential application of conversion factors expressed as fractions and arranged so that any dimensional unit appearing in both the numerator and denominator of any of the fractions can be canceled out until only the desired set of dimensional units is obtained. For example, 10 miles per hour can be converted to meters per second by using a sequence of conversion factors as shown below. 10 miles per 1 hour. And it said 10 miles per hour, but we've added expressly the 1 hour. I know that there's 1609.344 meters per mile. That's a conversion factor that you would be given or that you might be expected to know. Not here, but that's a conversion factor. Okay, awesome. And then, excuse me, 1 hour is 3,600 seconds. Again, conversion factor for that. Now, you may not be able to go from hours to seconds directly. You may have to go from hours to minutes and then minutes to seconds. I have to do it that way, and that's okay. Notice 10 miles times this thing per mile. The miles, one's on top, one's on bottom. I can cancel those. So I've gotten rid of the miles, and I now have an answer in meters per hour at that point. Now, I'm in the per hour. I multiply by this. I have 1 hour, this number of seconds. That cancels the hour. And so the units I'm left with are the meters and the seconds because I haven't canceled those. Since that's what I was looking for, meters per second, chances are this number is correct as long as I've got the conversion units right and I've done the math right on my calculator. So sometimes my calculator explodes and it blows up and it throws up on me and doesn't give me the number that I'm looking for. But if my units are right, chances are I've got it right anyway. Okay? One thing that I want to talk about while we're looking at this factor label method. What is my limiting significant number of digits? Well, 2. I have 2 here. I have a bunch here and a bunch here. Now, here's the thing about those bunches. We consider both this and this, since they are conversion factors, as infinitely precise. So we don't look at the number of digits that are here or the number of digits that are here. We only look at the one that we were given, this one. So realistically, this should be reported as 4.5 meters per second. Okay, that's the way it should be reported. We can look at a slightly more complicated thing, all right? I don't care that you understand what we're talking about with all of this stuff, okay? We talk about the definition of NOx concentration being in parts per million by volume. We talk about the molar mass as being in kilograms per kilojoule moles, okay? Or kilogram mole, sorry. Kilomole is the way that I typically see it. And the flow rate of the gas is being 20 cubic meters per minute, okay? The molar volume of gas is 0 degrees temperature. And 101.325 kilopascals is 22.414 meters per kilogram mole. And we can use all of this happy number, 10 parts per million. So 10 meters cubed per 10 to the 6 meters cubed. So that's what this is, 10 volumes per 10 to the 6 volumes. So as long as we're in the same units, it works. All right. So I have 10 meters cubed per meters cubed NOx over 10 meters cubed of gas, and it's 10 versus 10 to the 6. 20/1 meters cube of gas. This is this flow rate right here. So I can use that as a conversion. That gets me the meters cube of gas goes away here. And I'm left with meters cube NOx per minute. 60 minutes in an hour, that gets rid of the minutes. I'm left with meters cubed NOx per hour. Okay. I know that I have a molecular mass, or molar mass, of 46 kilogram per kilojoule moles. Okay, awesome. And since this is listed here this way, I have actually combined that with this number right here. All right. The molar volume of a gas is 22.414 meters cubed per kilogram mole. So instead of having this, I've put that in here. All right. That's that unit right there. I've used this as this unit right here. Awesome. And then I have the molar mass here. Okay. Now kilogram mole NOx, that cancels. I have the meter cubed NOx still from here. That cancels right there. Okay. I still have the kilograms of NOx because I haven't canceled that. And I still have the hours because I haven't canceled that. Now, I want to get rid of the kilograms because I want it in grams. So I have 1,000 grams per kilogram. That gets rid of the kilograms. Now that leaves 24.63 grams of NOx per hour. Okay. So I have canceled all of this stuff. Now, how did I know how to do that? Well, that's a bigger question. Realistically, I will use any unit that I can think of to get from where I am to where I need to go. And the question becomes, do I know enough things to get there? If I write it down, it gives me a way for me to be able to do that. Okay. So you'll see me do that. When I write out a particular problem, I will always write out exactly what I'm given and the units that it has and what the units that I want are. And then we figure out how do we get from one to the other. Okay. Here's another dimensional analysis example. Everything I have up here at the top are conversion factors. 1 mile is 5,280 feet, 5,280 feet per 1 mile. So this is the same thing. It's just flipped over. I have 60 minutes an hour, or 1 hour is 60 minutes. Again, same thing, just flipped over. 1 minute is 60 seconds, or 60 seconds in 1 minute. Okay, again, same thing, just flipped over. The reason that we've done that is because we want to be able to use the right conversion factor. So if I start in 50 miles per hour, right, and I want to end up in feet per second, then I need to find a way to get rid of the miles. So I use this unit right here to multiply. So 50 miles times 5,280 feet per mile. I get rid of the miles there, and that leaves me in feet per hour. Feet per hour is not what I want. I want feet per second. So I need to get rid of the hour. So I use this 1 hour because this is on the bottom. So I multiply by 1 hour is 60 minutes. That goes there. That cancels the hour, and that leaves me with feet per minute. I don't want feet per minute. I want feet per second. So I need to use this to get rid of the minutes. So minutes on the bottom here, minutes on the top here, and then that cancels. So that leaves me with feet per second, and it ends up being 73.3 feet per second. Does that make sense? I hope so. So examples, well, okay, let me see if I can find something. Bear with me just a minute. I'm going to stop sharing so that I can pull up an actual question that we should probably talk about. I love the waiting as I sit here and do this. Isn't it great? Okay, so I have pulled this up and I'm looking at, let's talk about this particular question. Brie was trying to make her favorite recipe, but was not sure of the conversions. What would you eat these cookies? So the recipe calls for 2¼ cups of flour, half a pound of chocolate chips, and 325 degrees Fahrenheit. Okay, awesome. So I'm going to come over here and I'm going to use my whiteboard and I'm going to show you that so that we can talk about how this is actually set up. Okay, I had a bunch of numbers. So, oh wait, hold on, wrong pointer. Two and a quarter cup flour. I have half a pound chocolate chips. And 325 degrees Fahrenheit. And I want to know, what does that look like in liters, grams, and Kelvin? Because she's made some conversions and we want to know if those are reasonable conversions. Because if they're not reasonable, then I shouldn't eat those cookies. So that's what I want to know. That's what this question is asking me. Now, offhand, I don't know any of those things. So I want to know, is it reasonable to talk about any of that? Well, okay, let's look at this. Oh, that's actually not what I wanted. Never mind. Oh my, I thought those were the actual conversion units. Okay, let's see if I have some. Nope. So let me see if I can find how many cups in 1 liter. Do we actually do this? Yeah, I do. So I found a conversion factor, and I'm going to write that conversion factor down on the whiteboard that I have. And I'll show you that in a couple of minutes that I've written all of these things down. I see that I have 1 pound, 453.592 grams. And then I want to go between and then I have this lovely equation to be able to do this. So 32 degrees Fahrenheit minus 32. the equation here, temperature in Kelvin equals temperature in Fahrenheit plus 459.67 times 5 ninths. Yahoo! So now I'm going to share my whiteboard again. You can see that I've written all of those factors over here, right? So if I want to look at my cups of flour first, I have 2 1/4 cups of flour. And actually, I'm not going to do it that way because I don't like fractions. And I apologize for how slow I am with this. .25 cup. Anything above the line is multiplied, anything below the line is divided. And then I know that 1 liter, which is what I'm looking for, is 4.22675 cups. And I can do the math on that. Sorry, bear with me just a second. I apologize. So now you should be able to see the calculator that I'm using. 2.25, and then I'm going to divide that by 4.2267, and that gives me 0.53. Okay, awesome. We can record that. Let's see if I can get the both. Five, three, two. And of course, since that's all I'm going to use it for is the 0.532, right? And I want to look and see, okay, comparative to the number that they gave me before, is that reasonable? So it said 0.5 liters of flour. Well, that's pretty accurate. Yeah, it's pretty close. All right, so this one, in my opinion, checks out. Awesome. Okay, so now I want to go from the 0.5 pounds of chocolate chips. 1 pound is 453.592 grams, because that's what I wrote over there. Awesome. And I can do that conversion again with my calculator. Woohoo. 0.5 times 453.592. Helps if you enter things right. (226.796) is my actual numerical answer, but my least number of sig figs is 1. So we're looking at roughly 200 grams, approximately 200 grams. And shocking, I don't have 200 grams is what she used. She used 2,000. That's a little off, so this is not a happy one. I'm going to say, no, I'm not going to use that. Thank you very much. Now, I could just stop there and say, I'm not going to eat those cookies. I could. But for the sake of argument, let's go ahead and talk about this last conversion, right? So I want to do 325 degrees Fahrenheit to Kelvin. So my temperature in Kelvin is equal to the temperature in degrees Fahrenheit, which is 325 plus 459 point something. What the heck did I write? 453.592. And then, of course, that was multiplied by, oh, sorry, 459.67. Wrote down the wrong thing. Looking at the wrong thing. Times 5 nines. And then I'm going to move this back so that we can see what we're actually doing here with the calculator. 325 plus 459.67 times 5 divided by 9. And that gives me 580. Awesome! 580! (580) Kelvin. Now, if I look at the numbers that she had, it was 373 Kelvin, and that's not right. Okay, and of course, just a smell test. I know that there's a big difference between those two. So the fact that those numbers are close means that that's probably not going to work. So those two things don't work. All right. So that's what we're talking about, is how do I find the conversion factors that I need? Sometimes that means looking around on tests or poking around into things that I have available to see what I've got that I could work with. Okay. So that's what we're talking about there. And I hope that works as far as dimensional analysis examples for those. As we continue through, there will be so many. So hopefully that takes care of it. Remember, everything should be done in the factor label method. So if you have units and you get your units to work to be what they should, then you should be okay. And while I'm sharing that screen, I'm going to show you that. So I got rid of the cups, and that left me with liters. I got rid of the pounds, and that left me with grams. And of course, this has no units on it, so as long as we've got that formula right, then we should be okay. All right? And now, to change completely from what we were doing to something else, isn't that entertaining? Let's talk about the atomic theory of matter. So, what does the atomic theory of matter tell me? Well, Elements are composed of extremely small particles called atoms. Those atoms are composed of small things. So all atoms of a given element are identical. They're the same size, the same mass, and the same chemical properties. Atoms of one element are different than another element. We know this. That's why we have a periodic table. Compounds are composed of atoms of more than one element for a given compound. The same types of atoms are present in the same number. So all CO2s have one carbon, two oxygens, that kind of thing. Chemical reactions rearrange the atoms, but does not create or destroy them. So that's the definition of a chemical reaction. Nuclear reactions are different. We will talk about those a little bit. What else are we talking about in terms of the atomic theory of matter? Well, we talk about the structure of the atom. So every atom contains three main particles that we want to be able to talk about. There are more, but we're just going to talk about those three: electrons, protons, and neutrons. Now, electrons were recognized by Thomson. They're negatively charged particles that are extremely small, and they're distributed throughout the atom. How they're distributed depends on who you're talking to and what theory we're looking at. For this way that we've done it, we just have valence shells, and we'll talk about that, both of those things later this semester. The protons were discovered by Rutherford. And again, I'm sorry for the yawning. They have a positive charge. They have the same number of protons as electrons, and therefore are electrically neutral. So for every positive, there is a negative, and are electrically neutral in the element form. Protons are larger than electrons and are called one atomic mass unit. They are centrally located, i.e. they're in this thing we call the nucleus, the center. And they contain approximately half the mass of the atom. All right, neutrons. The mass of each neutron is 1 AMU. Mass of all neutrons is just over half the mass of the atom. And the particles have no charge, so they're just pieces of mass. Now, what is their purpose here? Well, it's actually to provide a buffer between the protons that are present so that we can have things that stay together and are happy and not flying apart. All right, that's what we're talking about there. Where did my WebEx go? Not sharing. It's not helpful if I'm not sharing. So again, these are all the definitions that I gave you on slide 25. So elements, compounds, chemical reactions. So those are all on slide 25. On slide 26, we start talking about the atomic theory, the structure of the atom. Now, in order for these nuclei, as they continue to get larger, to stay together, we need mass to break up that positive charge. That's what the purpose of the neutron is, or at least that's how we talk about it. Now, you should know that the number of protons equals the number of electrons if the charge is neutral. You need to be able to draw this particular atom structure and identify each of the particles that are there, because they may not look exactly like that, but you need to know that the protons and the neutrons are in the nucleus, the electrons are around the outsides. Those are the things you need to be able to identify, okay? Now let's compare proton, neutron, electron. We said that a proton is positive, neutron is neutral, and an electron is negative, okay? So our symbol for proton is just the positive sign. The neutron is an N, and the electron is E minus, okay? That's again to indicate the charge. We know that the mass on the proton is approximately 1.0073. The mass of the neutron is 1.0087 atomic mass units. And the electron is way tiny, 5.486 times 10 to the minus 4th. So we typically ignore the number of electrons. It doesn't add significantly to the mass. And so the atomic mass is the sum of protons and neutrons. Okay, that's awesome. So they should all be whole numbers, right? And that should sit funny with you if you've ever looked at a periodic table, because they're not whole numbers. All right. Now, that's not everything that we have that makes up the atomic mass. And so we'll talk about that in a little bit. But if we're talking about a particular atom, it has a number of neutrons, a number of protons, and a number of electrons. We should be able to determine what its charge is. So if the protons and electrons are equal, that's great. If I have one less electron, it's a positive. If I have one more electron, it's negative. And I should be able to calculate the mass number, which is the proton plus the neutron. Okay. And we'll talk about that in a little bit. Things that have different number of neutrons are called isotopes, and that gets into nuclear chemistry, which we'll be talking about in just a minute. Questions on that? Hope not, but there we go. Isotopes. Oh, Lord. So we've got these symbols over here. 11/6 carbon. Yahoo. This symbol right here. This number at the top is called a mass number. The number at the bottom is an atomic number, and this C is the atomic symbol. So the atomic symbol and the atomic number go hand in hand. If I look on the periodic table and I find carbon, I see that carbon is C. Carbon has a number of 6. So the atomic number and the atomic symbol need to go together. If this number is 12, then the only thing that can appear as the atomic symbol is magnesium. Okay, that's it. They go together. All right, but this mass number can be any number of things. All right, now that mass number is made up of the atomic number and the number of neutrons. So if my mass number is 11 and I have 6 protons, I take 11 minus 6, that gives me 5 neutrons. Okay, I know that this is neutral. I have no charge on it. So the number of protons is 6. I have 6 electrons. Awesome. That's what that is. The only difference, if we go to a different mass number, so the 12, the 13, or the 14, this is carbon 12, this is carbon 13, this is carbon 14. The only difference is going to be in the number of neutrons. Number of protons stays the same, 6, which gives us carbon. Number of electrons stays the same, 6, because I have 6 protons, so I need 6 neutrons, because there is no charge on this. But the number of neutrons will change. So I take this mass number, 12, minus the atomic number, 6, and that's 6 neutrons. This mass number of 13 minus the atomic number, which is 6, that gives me 7, which is the number of neutrons. Mass number of 14 minus the atomic number of 6 gives me a number of neutrons as 8. So these are all neutral. So the number of protons and electrons is exactly equal. Number of electrons equals the atomic number. Okay? So atoms. Atoms are the smallest unit of a discernible material which we cannot break down without chemical changes. We have oxygen, we have carbon, we have nitrogen. Those can all be atoms. Okay? These are things that exist on the periodic table. Ions. Again, sorry for that. Ions. When an atom loses or gains electrons, the atom then has a charge since the number of protons and electrons are no longer equal. So we can talk about Cl minus, which is added an electron. So I know that Cl is number 17. I have 17 protons, and now I have 18 electrons, which gives me a net negative charge. O2 minus. Oxygen is number 8, so I have 8 protons, 8 electrons to start with. I add 2 additional electrons, and that gives me 10 electrons. Okay? Fe3 plus, if I look for Fe, I can see that he's number 26. So I have 26 protons, 26 electrons. If I lose 3 of those electrons, so I have 26 protons and 23 electrons, then it's an Fe3 plus. Okay, that's how we determine what those charges are. And it all has to do with the number of electrons that are on it. Okay, if I add additional electrons, 1 electron is one additional negative charge. 2 electrons is 2. If I lose electrons, then our charge goes up by 1. So plus 1, plus 2, plus 3. That tells me how many electrons I've lost. Molecules and molecular compounds. What are molecular substances? What does that even mean? They're made from nonmetals bonded to other nonmetals. They can be the same element as in O2 or different as in CO. Remember, we looked at those diagrams earlier. We had two of the same thing, and that was a compound. That's a molecule. It's a compound because it has two elements in it, okay? But they were both the same, so it could be O2. Or they could be different. We saw that before. We had 3 of one thing attached to 1 of another, and that would be something like NH3. That would work. All right. So compounds can be made of the same things or different things. They are considered molecules because they are multiple things bound together, and they are called compounds because they are not a single element. Okay. Now, use of atomic symbol and subscripts to convey the proportions of a compound. Molecular formulas are those that represent exactly how many of each atom are in the formula. For instance, H2O2, 2 hydrogens, 2 oxygens. So that's a molecular formula. Empirical formulas are the smallest whole number ratio of the atoms in the formula. For instance, HO is not the smallest whole number ratio. Or H2O2 is not the smallest whole number ratio. HO would be the smallest whole number ratio for that particular thing. So HO is the empirical formula of the molecular formula H2O2. Okay? Atomic masses. How do we determine the mass of an atom? First, we want to ignore the electrons. We talked about that before. They are so small that we can do that. We want to find the atomic number of the element. This is the number of protons, and it defines the chemical identity. Each proton counts for 1 mass unit. We determine the number of neutrons. You'll be told this. You'll be given a mass number so you can figure it out. Each neutron is also 1 mass unit. To get the mass number, we sum the protons and neutrons. And we always stop there. All right? That's where we go for a particular isotope. Now, the way that we get from that isotope to the numbers that we see on the periodic table is to multiply this number by the proportion of how often that isotope appears in nature. So we have carbon-12 and carbon-14. They exist in different proportions. We multiply the mass of each one by the proportion it exists at, and then add them all together. So 99% of carbon is carbon-12, 1% is carbon-13, and we do 99 times carbon times 12 for that, and 1 times 13, and then add them together to get the number that's on the periodic table. Okay? Does that make sense? I hope so. Questions, comments, problems, anything like that? Awesome. Well, that takes us to the end of Lecture 1. If you have any questions, comments, problems, whatever, again, please note the lecture number and the approximate time and what I was talking about, and send me an email or a question about that. And I will do my best to figure that out, okay, and get back to you as soon as I can. I appreciate you guys watching this. I hope you have a good day, and I will talk to you soon.